You know, water, everybody agrees, is going to be a huge problem. We're already short of water. I was in Israel in November. They have 2 huge desalination plants to supply Jerusalem with water. And what I want to show you is what I think is likely to happen, and it isn't going to be good. I don't want to scare you. I want to say we got to prepare for this. I think in the dry regions of the world, you know, they're important in 2 quite different ways. One is 40% of our grains are grown on irrigated land, and a lot of that water is being pumped up from below, and of course it's being mined. And when that runs out, we're in trouble. The other is that, 1.5 or 2 billion of our poorest people live in dry lands, and they're going to take a big hit. So we have to make a prediction of the future. And those of you who know anything about climate models, their great weakness is the hydrologic cycle. They try hard, brilliant people, huge computers, lots of different labs doing this, but the results are, you know, wishy-washy. If you look at how they predict change in rainfall for doubling CO2, there was a study made where it was 12 of these models, and they were compared. So they all ran the same scenario, and if everything was fine, they get the same answer. They got quite different answers. They did agree on one thing, at least on the sign, you know, whether it's going to get wetter or drier, and that is that the tropics are going to get wetter and the immediate extratropics are going to get drier. Well, tropics don't need to get wetter, and the extratropics certainly don't need to get drier. Then they show that for other regions of the world, like our American West, they leave that white, which means that some models said it was going to get wetter and some said it would be drier. Further, if you look at the tropical part, they agree in sign, but they disagree widely in magnitude of the change. So that's really our best tool to find out about the future, and so far it's not really up to the task. So thanks to this gentleman, that's me in the white shirt in 1955, and as a graduate student at Columbia. I got interested in water and have a different way to look at it, which I think tells us some very interesting things. What I'm going to tell you is about 3 archives that tell us something about how rainfall has changed. One of them is closed basin lakes. The Dead Sea is a closed basin lake. Great Salt Lake is a closed basin lake. These are water bodies that receive, mainly supplied by rivers, and they lose all the water by evaporation. And so their sizes reflect the hydrologic conditions, a combination of runoff, rainfall, and evaporation. So when they're big, it's wetter, and when they're small, it's drier. Another archive is stalagmites in caves. The oxygen isotope composition of the calcite in those stalagmites tell us about the strength of monsoons. Very important. The third archive, I'll just briefly mention at the end, is ice cores. Ice cores in polar regions give us a record of gas composition of the atmosphere, because the ice contains initially about 10% bubbles, and these are pristine air. So lots of things have been learned by doing isotopes and gas compositions. So another record is interestingly enough, the isotopic composition of the oxygen gas that's in these bubbles. Okay, so that's what we're going to look at. the bottom line is that what this information tells us is that the world's hydrologic system, especially that involves monsoons, is highly orchestrated. So one place gets wetter, another gets drier. It's absolutely amazing, and it's very interesting. We're going to see that when it was colder in the glacial periods, the lakes at 40 degrees north, the closed basin lakes were much larger, very much larger. So if you invert and say if it's larger when it's cold, it'll be smaller when it's warm. That's a guess. The other thing is that during the period of deglaciation, when we went from full glaciation into full interglaciation, there were incredible changes, oscillations that involve my conveyor, and they shifted the thermal equator back and forth, which pulled the rain belt back and forth with it, and it made very large changes in the hydrology of drylands, and I'll show you some of that. So you might say, what does that have to do with the future? Well, what it has to do is that as we warm the planet, we're going to warm in the transient, which is going to be a long transient because, the CO2 is going to just keep building up for a long time. The northern hemisphere is going to warm twice as fast as the southern hemisphere. All models say that, and that's simply the result of the fact that there's more land, twice as much land in the north there in the south. So the great heat capacity of the ocean keeps the south from warming as fast, and that means that the thermal equator is going to shift. By thermal equator, by definition, is where you stop getting warmer as you go, toward the equator and start getting colder again, and that moves back and forth. The rain belts, as I'll show you, are centered on that. Now, let's get to this. This is a stroke of luck. When I started Columbia, I think you decided, was it 1954 or 5 that I gave that talk out in? 55. So I got to Lamont in the summer of 52, and I was between my junior and senior year. And I went finished my college education at Columbia College, and then went to graduate school. So 2 years into graduate school, my professor was supposed to give a lecture at the Great Basin Archaeological Society, which was meeting at the Southwest Museum in very close to Pasadena, but I guess in Los Angeles. And at the last minute, he decided he didn't want to go, and he sent me. And so I flew out on a prop plane, got there, it was 104. I think it was the hottest days that they've ever experienced. And of course, the museum wasn't air conditioned. I was petrified that I had to give a talk because I was the kind of kid that, speech class was a great trauma to me. But anyway, I started talking, and I realized I'm talking about radiocarbon dating that I happened to know by that time an awful lot about. And I suddenly relaxed. I felt real good about it. And I don't know how good a talk it was, but at least I got through it. And at the end, this guy came up to me. It was lunch break. And he walked up to the podium, and he looked up at me, and he said, "Look, kid," he said, "I can see you know a lot about math and physics, but I also can see you don't know a goddamn thing about the Earth." He said, "You come with me for 3 weeks, and I'll change your life." And so I said, "Well, I don't have any money." And he said, "I'll pay everything." Now, this guy, is somewhat of an opportunist. He knew that I could get him free radiocarbon dates. At the time, it was hard to get any radiocarbon dates very early. And so I called up my wife, and she said, well, if he's going to change your life, maybe it's a good thing. You should go along with him. So I went along, and he took me to this place. That's if you go to Reno, Nevada, and drive about 45 minutes, or now it's an hour because they built so many subdivisions, to the northeast, you come to a beautiful Pyramid Lake. And he took me there. It's named for a pyramid that sits near the eastern shore. That's calcium carbonate from hot springs. The island out in the middle, I collected my first samples because he was interested in finding out when this lake was much larger than it is now. And at its, when it was deepest and biggest, it just about capped that island out there. That island, as you see in the photograph there. And so I collected calcium carbonate tufas and thereby got interested in the history of this lake. Now, well, let's go back one more. This is the Great Basin. So Pyramid Lake, you can see, is named there. It's a tiny little lake now. Great Salt Lake is much bigger. They lie at the extreme sides of the what's called the Great Basin. It has no outlet to the sea, so any rain that falls in there has to evaporate within the basin. During late glacial time, those lakes got as big as the blue. Now that's amazing. So the white are the little lakes that are left, and that was what they were like before irrigation started to steal the water. So they're all a little bit smaller. But you can see the cover just by eye was 10 times greater. So these are the reason they were great recorders. They're like reservoirs. So that in a sense, it's like when you look at Lake Mead or something like that and it gets very small, you know there's been a serious drought. They're using water and it's not being replenished. So these lakes were 10 times larger. Now it's really hard to understand. Can't have been 10 times more rainfall. That's ridiculous. So it may have been twice as much rainfall. It was colder. There's probably somewhat less evaporation. But a very important thing in an area like this, and it's important now, is that the amount of water of rainfall that falls on the dry land that runs off is a very strong function of the amount of rainfall. So the drier it is, the smaller the fraction. So where I live, where you live here, or right here, about 50% of the rainwater runs off to the sea. In the Great Basin, probably running into these lakes is, even though the water's coming out of the mountains, maybe 8%. So it's a great amplifier. So it makes it harder to back out exactly what the conditions were. On the other hand, it makes them very sensitive recorders. A lot of radiocarbon dating has been done on the lake. You probably can't read the scale on the little insert there, but it starts at about 30,000 years and goes to about 15,000 year radiocarbon. That's the time of the last peak glaciation. That's when mountain glaciers were the biggest and the Laurentian ice sheet was at its biggest. And then starting at that gray band, we got these oscillations. So it's a deglaciation. I'll show you more about that. But first of all, let's just consider how big these lakes were. So we see the red is what they were at their maximum in the Holocene. And there, as I said, in 1850, that big one, the Carson Sink, was more or less dry. So if you subtract that, you've got very small lakes. The pale blue, or whatever it is there, gray, that's the size of the lake during full glacial time. And then the grand finale during deglaciation, which we'll get to, it got much larger and it was the dark blue. We'll get to that. So why was this lake so large? That lake that we just looked at is more or less where the red dot is, and the big ice sheet's there. So most people who studied it have said that this big ice sheet is the cause. It deflected the jet stream, and that made that lake so big during glacial time. So we did a study. We went down. I formed a group 2 or 3 years ago saying, hey, we can do more than look at the history of these lakes. Let's try to use this to say something about how climate affects water availability. So we went to 40 degrees south, and that's the only place on the planet where there's a closed basin lake at that latitude. And we found that there's another smaller lake, but the red shows what it is today. The pale blue shows what it was during glacial period by radiocarbon dating. And unfortunately, we searched the shoreline for the dark blue, and we didn't find anything that's datable. We suspect that it's younger, but we can't say. Now, so we have 40 degrees, 40 north and south in the Americas. And Elizabeth, my wife, and I were in Israel, and they were busily drilling a hole, 450-meter core in the center of the Dead Sea. It's going to be a wonderful record. But they already know from raised shorelines, where they have beautiful record, probably better than record anywhere else in the world, that the Dead Sea during glacial time, just like the lake in Nevada, was about 4 times bigger than it is now. So some of you know there's the Sea of Galilee, Kinneret up at the top, and then the Jordan River, and then the Dead Sea. That was all one big lake, and very well dated. So in China, at 40 degrees in China, there's not, what I would say is not firm evidence, but fairly good evidence that the same was true there, big lakes. So for some reason, when it was cold, the lakes were much bigger. Now, let's jump to what went on during the deglaciation. So this is a record from an Antarctic ice core, and it shows 3 things. On top is a record of stable isotopes in the ice. That's related to air temperature over Antarctica. In the middle, the red is the CO2 content of bubbles, and the bottom is the methane content of the same bubbles. And there's been a slight displacement to correct for the fact that the bubbles formed deep in the firn. We don't need to go into that. What this shows is the upper 2 show that the main glacial period, when it was cold and low CO2, came to an end about 17,500 calendar years ago. And the CO2 started to come up, the temperature of Antarctica started to come up, and then one of these oscillations occurred, and both stalled. And there's sort of a plateau, or maybe a slight reversal. And then during what we call the Younger Dryas, the warming resumed, and the CO2 rise resumed. Meanwhile, in the northern hemisphere, things were totally different. The methane record, I use the southern methane record because it allows us to tie the northern cores to the southern cores. The methane record in Greenland would be exactly the same as this one, because methane mixes very quickly from one end of the planet to the other. And what it shows is that you get something that stayed cold, if we looked at the temperature in Greenland, until about 14,000 years ago, and then it got very warm, stayed warm a while, and then there was a big relapse. So in a sense, there's some sort of anti-phasing between what was going on in the north and the south. That had to do with the fact, and I don't want to get into this too much, that during those cold phases in the north, the conveyor circulation that I invented, I guess, shut down. And when it shut down under cold conditions, you got sea ice forming. It could form in the next winter because you'd cap that region off with fresh water at the surface, like is present in the Arctic today. You get sea ice, and that makes a huge difference because instead of having ocean heat coming out, warming up Norway and other areas up there, all that heat is blocked. It can't come through the ice. Further, any sunlight that got there in the winter would be reflected back. So that would make that area like Siberia. And so we think that the winters got fearfully cold there because we have a record from the ice core shown by the red dot on the 2004 diagram there, that indicates the mean annual temperature during the last of these cold phases, the Younger Dryas, was about 15 degrees colder. But from mountain glaciers on the eastern side, the other red dot, we could show that the summer temperatures changed only about 5 degrees. So the only way that could, if they're both right, you'd have to have fearfully cold winter temperatures, and we think that's true. Now, what that did was amazing. This is the rain belt. And of course, the Amazon, the wet place, it sits within the rain belt. The rain belt, the tropical rain belt, is wide today over the continents and narrow over the oceans, as shown. It's wider on the continents because of the low heat capacity. I won't get into that. We have records at all 4 of those red points, and I'll only show you the record from the diamond, which is up on Altiplano. But what it shows is that when there was a lot of sea ice in the north that pushed the thermal equator to the south, and the river flow off of Venezuela at the triangle dropped way down because the tropical rain belt moved to the south. The river, the runoff over at the red circle got much greater. Caves that are dry now and were dry most of the time got wet at the square. And then up in the Altiplano, the lakes did exactly the same thing as they did in Nevada. Now up on that Altiplano, you have big Lake Titicaca, and to the south, you've got little Lake Popu, or however you pronounce it, and big, what they call salars, which are playas where there once was a lake and now it's dry. That's where the villain in the second to last James Bond movie died at the end, as those of you who wasted your time seeing that movie. So the Lake Poopoo is shown. I have a blow up now of this area down in the southern part of the Altiplano. And so that lake now is a little red place. During peak glacial time, it was the pale color. And during the first phase of the CO2 rise, that lake got very large. So it was at its largest. And this is because the rain belt is pushed to the south. I want to make the point now that the whole system is orchestrated. And to do that, I have to show you records of monsoon rainfall in China. There's a scientist at the University of Minnesota who's, I'm sure, going to get in the National Academy this year, named Larry Edwards, who has perfected the dating of these stalagmites using uranium series isotopes to just a masterpiece. At 100,000 years, he can get ages as accurate as 60 years. It's amazing. I mean, it's wonderful. And so he has gotten an oxygen isotope record that in this case, and he's got it further back, but it doesn't matter, back to about 225,000 years. And shown above that, or on it, is a red curve. That's summer insolation it's calculated from the orbital changes of the Earth, which can be done to a gnat's eyebrow, both in magnitude and in timing. And you can see that there's the summer insolation is obviously is orchestrating that curve. And it turns out that the interpretation is that when the oxygen isotope are negative, that's strong monsoons. So that as the strength of summer insolation was high, and that's sort of a 20,000-year frequency, it has to do with the precession of the Earth's orbit, you get strong monsoons, and then at the other part of the cycle, you get weak monsoons. But if you look at that last cycle, that's the time interval we were talking about, the deglaciations. What you see is that if I were to compare it to the Greenland ice core, well, I do, but forget that for a minute. There are two periods of very weak monsoons. One is at about 16,000 to 15,000. The other is about 12.7 to 11.7. That's these are the two times those lakes on the Altiplano were very large. So when the lake in Nevada was very large, the monsoons in China were very weak. The lakes on the Altiplano were very large. The caves in Brazil were very wet, where they're normally dry. So now one more thing, and I'll draw some conclusions. One of my former students, and this was the model for that terrible movie about the conveyor, Jeff Severinghaus, his roommate, when he was first at La Jolla at Scripps, was Michael Molitor, who was an advisor for making that film. And we're sure that Jeff Severinghaus was the model. Turns out Jeff Severinghaus is one of the best scientists on the planet. He's doing really remarkable things. This is a record from ice cores, shown in red, of the oxygen isotopic composition of oxygen gas trapped in the bubbles in the ice. And what Jeff did is to translate that red curve into the purple curve above it, and he had to take into account that all the plant life on the planet produces an amount of oxygen equal to that in the atmosphere about once every millennium. So when you look at the red curve, you're looking at integration over 1,000 years. So essentially, he took the first derivative, not quite that simple, to get the instantaneous oxygen isotopic composition of the oxygen being produced at a given time, and that's the purple curve. So that's something to do with all the oxygen in the Earth's atmosphere. Above it is Larry Edwards' record of the strength of the monsoons in China. And there's a little offset in that, which has to do with different dating of one record than the other. When those are reconciled, there'll be a perfect match. You can see it by eye, that for every peak in one, there's a peak in the other. So what that says is that that these changes are probably reflecting the changes in the strength of the monsoons in the northern hemisphere. Of course, you have to think that there's someplace else where when the monsoons were strong in the weak in the northern hemisphere, they were strong in the southern. But since the northern hemisphere has so much more vegetation and land area, so much more monsoon-driven plant growth, that it is the thing that's making the difference here. So what he has shown is that this whole Earth's hydrologic system is orchestrated, and it's changing together, and it's changing big time. These are not small changes. These are huge changes. So as far as saying what's going to happen in the future, well, maybe it's hard to predict even the sense, but it would be incredible if the changes weren't of this magnitude. I mean, the forcing in the glacial time, the cooling in the glacial time is comparable to what we're going to do in the next 100 years. We're going to warm the planet by at least 3.5 degrees if the models are correct, maybe 4 or 5 degrees. And we think that the cooling during glacial time was about that. So take-home message is that at these latitudes of 40 degrees and in some of the tropical areas like the Altiplano have shown that the hydrologic conditions are very sensitive to these small climate changes. And I said that one way to look at it is if colder climates made more rainfall and runoff, then perhaps warmer climates are going to go the other direction. I firmly believe that's what's going to happen. So these areas are going to get very dry. I'll give you an example in a second. And as the thermal equator shifts, we're going to see the same kind of thing, and it's going to go in the opposite direction. So instead of moving south, it's going to move north because we're going to warm the northern part of the planet faster than the southern part. Now, you might say, well, have we seen any of this kind of stuff during the Holocene, which is the last 10,000 years? And it's a much harder period of time to study, but I'll just give you 2 examples. This is the West Walker River. It feeds one of those little lakes south of Pyramid Lake, Walker Lake. And you see those stumps. Actually, there are 84 of those stumps. They're Jeffrey pine. Scott Stein discovered these one August when the river was low. Those trees have 120 rings in them. That kind of tree is killed with a few months root drowning. So he lived 120 years, and there's no way in hell that river was running through there, and there's no other place for it to go. So that area was very dry. And the time based on radiocarbon was the latter part of what we call a medieval warm, time when the Norsemen were in Greenland. Scott Stein has 5 other places in, let's say, within 100 miles of Lake Tahoe that show the same thing at the same time. There were 2 of these droughts that were century long. Their intensity was greater than any 5-year drought that has happened in historic time. So this was a time when we can't, this whole climate gate argument was about whether the medieval warm was as warm as what we got now. The tree ring people were saying that it's warmer now than it was in the medieval warm. I don't believe that. I don't really think we can do it that well. But it wasn't, it was close to what it is now, and yet we had this enormous drought. A young man named Aaron Putnam went last summer to far western China where the Silk Road went through. And he was trying to study glacial moraines, but the local chieftain, or whatever they call him, wouldn't let him go up in the valley. So he spent his time looking around the desert. And he found two things. He found this sand plain in westernmost China, sticking out of sand that was that thick were all kinds of tree stumps. And then there's a shoreline of a huge lake in there that's now represented by a swamp about 10% the size of the lake. And he found shells on the shoreline that could be dated. So with Elizabeth's help, he got dates. Now he has about 15 radiocarbon dates, and they span the length of the Little Ice Age. And so it clearly was considerably wetter in that area during the Little Ice Age than it is now. So these are sort of anecdotal evidence that we can have big hydrologic changes when there is rather small climate change. This is scary. And we're about to make a much bigger climate change. And so it's my opinion that we're going to see very large hydrologic changes, and we're going to run CO2, I would say, to at least 700 parts per million, unless the world really wakes up and gets to it to do something. And therefore, we're going to see pronounced climate changes. I hate the use of the word catastrophe. I think that this is not going to kill people, but it's going to make a horrible mess of the ecology of the planet. And I think in these drylands, it's going to make a huge difference in water availability, which will affect agriculture and will affect the livelihood of the poor people that live there. So it's something we better start to think about, how we're going to react to all of the implications of this. Agriculturalists say that for every degree that we heat the planet, the yield of grains could go down 10%, that they're all growing beyond their thermal optimum. The population is going to increase by 20 or 30%. And if those happen over the same time scale, then, you know, if we're growing the same crops in the same place, the food availability per capita on the planet is going to be half what it is now. Well, I suppose we can compensate some way, but it's not going to be so simple. So we're headed for dangerous territory, and we're going to, 5 years ago, I would said we could avoid it. Now I said we're not. If I'd given my other talk, the scenario I see, and you can ask questions about it afterwards, that the time that's going to elapse between where we are now and when we get all of our energy from non-fossil fuel sources is quite long. Nobody knows how long, but it's long enough that CO2 is going to build way up. So at some point, I believe firmly that we're going to start pulling CO2 back out of the air. And fortunately, Klaus Lochner at Columbia knows how to do that. It's certainly technically feasible to do it. But it's still going to get hot enough, I think, that there's going to be very strong temptation to take the next technological step, and that is putting SO2 in the stratosphere to change the albedo to cool the planet off. And these are interim things that, you know, people on the planet may demand while we're waiting to get into the wonderful world where we get all of our energy from the sun, which is certainly possible, and we'll get there. But it's going to be a very interesting time. I'm 79 and a half, and I wish I could live to see it, but I think, even if I lived to 105, I wouldn't quite make it. So I won't see it, but some of you will. Thank you.